Good afternoon, everybody. We're looking at a classic game in game theory, police versus guerrillas. And let's check this out. So what's going on is we have a police, they represent the government. We have an insurgency, the guerrillas, and and so there are two arsenals that are filled with weapons and ammunition that the guerrillas would like to take, and either one will do. They don't care which. If they can take both, that's great, but what they'd like is to get one, so then they have a nice resupply. They have weapons, they have ammunition to continue the insurgency. And of course, the police want to defend both of those arsenals, all right? So neither the players both know the night the attack will take place, but they don't know where the other player will send their forces. Okay, so they have to make a strategy and then go for it. And the police don't know exactly where the guerrillas are going to concentrate their attack or if they're going to divide their forces evenly, and the guerrillas don't know how the police will try to defend. All right, so the police hold an arsenal if they have at least as many defenders there as attacking units. Okay, so if they're attacked with 3 units and they have 3 units or more there, they hold it. Okay, and so, like, for instance, if they have 4 units, they can have a strategy like 3-1. And what they're going to do is they're going to randomly select which arsenal to send the 3 units to and which arsenal to send the 1 unit to, right? So they have the strategy 3-1, but the 3 could go to either arsenal. It depends on the randomization. And then suppose the guerrillas have 3 units, which what they can attack, and they could play a strategy like 2-1, where they send 2 attacking units to an arsenal and 1 attacking unit to the other arsenal. But again, they're going to randomize which arsenal gets the which force attacking. All right, so if you look at it, 3-1 versus 2-1, well, half the times the police will hold, right? Because they'll have 1 unit where they're attacked with 1 unit, and they'll have 3 units where they're attacked with 2 units, and they'll hold. But what if they get it wrong? What if their randomization sends 3 units to where the 1 unit attacks, which is fine, they'll hold that arsenal, but they'll only have 1 unit where 2 units attack, and that arsenal will be lost. So the 3-1 versus 2-1 strategy, the expected value of repeated number of plays is 1/2, right? One when the police hold it, that happens half the time, and 0 when the guerrillas take one. So the expected value turns out to be um, 1/2, and that's the game value inside the matrix. Okay, so you kind of see how it works. The police have P units, the guerrillas have G units, and if the police have more than double the amount of guerrillas, they can just divide their forces equally, and the guerrillas don't have enough forces to take either arsenal, right? But if the guerrillas have more than the police, they can always win. They just group all of their units together and send it to one arsenal, right? So there are some constraints here that means that the only games that we really have to solve, right? The only games where there's really a something there, some meat on the bone, is when the number of police is greater than a number of guerrillas, but it's not equal to or greater than 2G. All right. So these will be the games which are interesting and will have something to solve. All right. So um, let's take a look at the 3 police versus 2 guerrillas game. And first, just to understand what all the strategies should be, right? The police have only two distinct strategies, 3-0 and 2-1. And you might say, well, there's also 1-2 and there's also 0-3. But my contention would be, well, when we randomize the 3-0, it could be either this one or this one, right? It depends. With the 3-0, we're gonna randomize which arsenal gets the larger number of forces sent to it. All right. The same with 2-1, right? Since we're randomizing the 2-1, we don't need the strategy 1-2. Okay, it's gonna get played. We're gonna send the larger force to both arsenals if we play this repeatedly over time. So there are only two distinct strategies, right? The other two come along for the ride because of the random way at which we're choosing where to send our larger force. And the same is going to be true for the guerrillas, right? The guerrillas have two units. They can either send them all to one or they can divide them equally, 1-1, right? And again, 0-2, we're not gonna worry about the strategy 0-2 because it's taken care of by randomization of the 2-0 strategy, right? So those are the strategies, and so then the game matrix is going to show those strategies. The police player gets 1 for a win. The guerrillas player gets 0 for a win. So we're going to put the guerrillas as the column player because the guerrillas are trying to minimize, right? A win for them is a loss for the police. So in our typical non-zero, excuse me, zero-sum game matrix payouts, right? The row player is maximizing, the column player is minimizing, and this setup gets it just about right. Police as the row player, guerrillas as the column player. All right, and how are we going to solve this? All right, so um, and let's just verify these, right? So if the police play 2-1 and the guerrillas play 1-1, well, the police always have at least one unit at both arsenals. So they always win. So that's a 1. Okay. We talked about these randomizations, right? So if the police play 2-1 and the guerrillas play 2-0, well, half the time the police have two units where they get attacked. But the other half of the time, they only have one unit and they get attacked with two and they lose. So that expected value is a half. That's why the payoff there for that entry is a half. Same with 3-0 versus 2-0, right? Whenever the police guess correctly and send 3 units to defend an arsenal that gets attacked, they win. But half the time they've chosen the wrong arsenal to defend. They have 0 defenders where 2 attacking units hit. So half the time they lose. So again, the expected value there is 1/2. And then 3-0 versus 1-0. Ooh, this looks to be a problem. Oh yeah, I'm sorry. It's a it's a 0. It's a loss for the police because they play 3-0 and they leave one arsenal undefended. And the guerrillas, having split their forces, are attacking each arsenal with at least one unit. So no matter how the police randomize, how the randomization works out, the 3-0 loses to the 1-1. All right, so that explains how we set up the game matrix, and now the question is, can we solve the game? And I hope you're thinking yes. I hope you're seeing some things that lead you to believe yes. So looking at the Data Hub notebook I created for you, I did bring some of the information over, right? But we have this, and the first thing I want you to notice is there's domination, right? That the police prefer 2-1 to 3-1 in every case. Why? Because if the guerrillas play 2-0, it's the same outcome, 1/2 versus 1/2. But if the guerrillas play their strategy 1-1, then the police do a lot better, 1 versus 0, if they choose police 2-1. All right, so the first thing we're going to write about this situation, right, and make sure that this is a markdown cell. Oops. Okay, markdown cell, right, is we're going to say that police, and then I'm going to use text via, wait, I don't need to do that because we're in a notebook. I can type double asterisk for bold, right? So I'm going to go police 2-1, right, dominates police 3-0. And I'm going to have some bold in there just to make it easy to identify the situation. But what should be clear is that the police will never play their dominated strategy. Okay, well, if the police say, nope, we're never going to use this one, then the police are playing 2-1, and the guerrillas know what their choices are. If they split their forces equally, they get beat every time. Their only chance to hold half the time, excuse me, to overtake one of the arsenals half the time is to play their 2-0 strategy, all right? So, right, when the, let me again switch to Markdown. Um, so the Guerrillas are choosing between losing all the time, right, and that's the one, or winning half the time, right, by getting a half, right? Thus, they will choose Guerrillas 2-0. Okay, so now we know that the optimal strategy choices, right? We know that the Guerrillas will only play 2-0 because the police are only playing 2-1, and so we know the value of the game is a half. And we've got all three things. We know that the police always play 2-1, the Guerrillas always play 2-0, and the value of the game is a half. So let's put that in. And B equals fraction 1/2. Is my dollar sign. Wait. And markdown. And there we go. All right. We know what's going to happen now. Okay. So this slide rehearses what we did on the notebook page, right? And so we see the police always play 2-1 and the Guerrillas play 2-0 with the game value equal to 1/2. All right, so that's a very simple version of the game, and let's look at another one. So let's look at 5 police versus 4 guerrillas, right? Now, the police always win when they play 3-2, but the guerrillas play 2-2. Why? Because the guerrillas are never sending more than 2 attacking units to either arsenal, and 3-2 means the police always have at least 2 units there. Now, when the guerrillas split their forces into 3-1, they win half the time. They lose at the arsenal if they lose at both arsenals if they send 3 attackers to the arsenal that's defended by 3 police, right? But if it randomizes the other way and they send the 3 attackers to where the police only have 2 defenders, they win. So that expected value is 1/2. Here, the guerrillas are always sending at least 4 units to 1 arsenal, and the arsenal is only protected by 3 and 2 units respectively, so they always win, right? They always win against 4-1 with 2-2 because they're always sending at least 2 attacking units, and they'll take the arsenal that's only defended by 1 police unit. Okay, 3-1 versus 4-1. Again, if this randomizes correctly for the police, half the time they hold. But if it randomizes incorrectly, they lose. So the expected value is a half. And the same thing holds true here. If they send the 4 units to the right location, half the time they hold. But the other half of the time where the 4 units go to the wrong location, they lose. So expected value is a half. Notice that when the police play 5-0, any split at all from the guerrillas means they win all the time because they attack the undefended unit with at least 1 attacking unit. 5-0 versus 4-0 splits up to 1/2. Again, if it randomizes correctly, the police win. If it randomizes incorrectly for the police, the guerrillas win. So creating the game matrix goes like that you have to reason through the expected values and think about what's going to happen. Okay, so solving it though is the same as before, at least in this case. Right, let's look at it, okay? Well, if you'll notice, right, that police 4-1 dominates police 5-0, right? We have 0 compared to 0, a half compared to 0, and a half compared to a half. So 2 of them are the same, 1 of them is better. So we know that police 4-1 dominates. Okay, so police 4-1 dominates police 5-0. But that means, right, that the police will never play it. So we're essentially deleting a row, right? We can delete the 5-0 row. Why? Because the police will never play it. All right. Notice there's no dominance between police 3-2 and police 4-1, right? So we can't delete there. But at the second point, right, we notice what? We notice that there's dominance here for the Guerrillas because 4-0 dominates one half, one half. So let me first get rid of this. I'm going to jump in here and do what? I'm going to jump in here and I'm going to grab this game matrix. Why? Because I want to get rid of the 5-0 strategy. And I'll make that markdown and maybe it'll work better. There we go. And let me, so, so we've decided that right, since the 5-0 strategy is dominated, we'll just delete it, and then I'm left with this, right? But in this one, notice that 3-1 dominates 4-0. Okay, so let's get rid of some stray markings there. So what am I going to do? I'm going to get rid of 4-0, right? And how do I do that? Well, I'll get rid of the strategy in the strategy list, and then I'll get rid of the last 0, right? And here, get rid of the last 1/2. And there we go. And let's see if I did it right? Because we wanted to get rid of 5-0. And I did this backwards, right? Because 3-1 dominates 4-0, and I got rid of 4-0, right? I forgot that we're minimizing and zero's better than a half. So what am I going to do? Um, so one of the cool things is I'm hitting Control Z. Why? Because I screwed up and I want my matrix back, and Control Z is edit undo. So for some period of minutes after you've changed the text in a markdown cell, you can hit Control Z and undo. Okay, it doesn't last forever, but for a few minutes you do have that option. So what I need to do is I need to get rid of the 3-0 strategy. All right, so let me actually do it this way. So we know that Guerrillas 3-1 dominates Guerrillas 4-0. Okay, which means what? Which means I'm going to take this game matrix and reduce it again. And this time I'm going to get rid of what? Okay, I've got to remember, right, that it is time to get rid of 3-1. 4-0 is better, so I want to get rid of 3-1. So I'm going to take out 3-1 out of the title row. I'm going to take the middle option out of the next row and take the middle option out of the final row. Let's see if I finally got that right. Okay, so 5-0 is dominated for the police. 3-1 is dominated for the Guerrillas. So I should have 1-0-0, 1/2. And I have made a mistake. I got rid of the 1 instead of the 1/2. But that can be fixed. Let me jump back in here. And so this should be a 1, not a 1/2. Let's get it right. Okay. And now I do have it correct, right? That in the 2-2 column for Guerrillas, 1 and 0 are the payoffs. And in the 4-0 column for the Guerrillas, 0 and 1/2 are the payoffs. And there's not dominance, right? I can't solve this one by dominance. Okay, why? Well, look, right? There is no dominance. The Guerrillas, they would strongly prefer 2-2 to 4-0 if the police play 3-2, but if the police play 4-1, they prefer the 4-0 strategy, right? Um, so the something's wrong here. 2-2 versus 4-1 isn't zero. Oh yeah, it is. Okay, that's right. That's right. I'm just trying to make sure I get this right every time. Okay. Um, so what do we need to do? We're going to solve it with oddments is the key, right? Um, so oddments, and they're the same for both players. If you'll notice, there is no difference in the calculation, right? So what am I going to do? I'm going to do oddments 1 minus 0. The absolute value of 1 minus 0 is 1. The other oddment is 0. The absolute value of 0 minus a half, right, which equals a half. Let's just look at this for a second. Make sure it's marked down. And let's take a look, right? Well, what am I doing? Remember, I'm adding them together in the denominator. So the denominator is 3 halves, and then the two numerators are 1 half and 1. Okay, so the optimal strategy mixture is what? Okay, well, it's going to be this fraction. Um, Let me think about this. I suppose I want a vector here. So let me do that. Vector R will do Rose's strategies first. And I'm going to do left and the square brackets. I'm going to do right and the square brackets. And then inside I'm going to do the begin array, but it's just a column vector, right? So I just need one. And then I'm going to do end array. And then what am I going to put in the middle? I'm going to put fraction and then close off that line. And the second element is going to be a fraction. Okay. So in the first fraction, remember I'm reversing the order. So in the first fraction, the top of the first fraction is 1 half. Let me just put it in as 1 slash a half over 3 halves for the moment, right? And the second one is 1 over 3 halves. Okay. And if you look at this carefully, you see that in the top component, the 2's cancel, right? 1 over 2 divided by 3 over 2. When I invert and multiply, I have 2 over 3. The 2 in the numerator cancels with the 2 in the denominator. And this ends up being 1/3. 1 over 3 halves, that's the reciprocal of 3 halves, which is 2/3. And I'm sorry, my 3 looks a little wonky up there. But when I actually do the fraction computation, right, I see that this becomes, and let me just copy paste it. Why? Well, it's close to what I need, except in the top of this fraction, right, I need 1/3. Sorry, that was 2/3. That's the denominator. And the numerator is 1/3, right? Yes, the numerator is 1/3, the denominator is 2/3. And that's also true for C, right? So I can go ahead and say, hey, well, that's also equal to, let's see, backslash effect C. So both the guerrillas and the police should randomize and send 1/3 of the troops, excuse me, how to say this. They should each choose, the guerrillas, if they're playing 1/3, 2/3, should 1/3 of the time play the 2-2 strategy and 2/3 of the time play the 4-0 strategy, right? And the police, 1/3 of the time, should play the 3-2 strategy, and 2/3 of the time should play the 4-1 strategy, right? That's what we're finding, all right? And then what's the value of the game? Well, if the guerrillas are playing 1/3, 2/3, right, and the police are also playing 1/3, 2/3, how do we decide what the value of this game is? Well, let's focus on, right, let's say the guerrillas play 2-2, right? Then 1/3 of the time the police play 3-2 and win one, right? So we have 1/3 of the time they get one, right? And 2/3 of the time they play the 4-1 strategy and get zero. Okay, so that's 1/3. What about the 4-0? Well, if the guerrillas play 4-0, they get 1/3 zero. 1/3 of the time they get zero. 2/3 of the time they get 1/2. The twos cancel. That's also 1/3. So if I look at this in terms of, and think about the expected value, given that both players are randomizing, and they're not just randomizing their strategies, they're randomizing within their strategies which arsenal gets sent the larger force, right? So there's two different randomizations going on. But when you take care of it, you realize, oh, the value equals 1/3. All right, so let me get rid of all of that. And, sorry, I can just do V equals 1/3. Make that a markdown cell so it displays properly, and we're good to go there. All right, so the key difference here is we want to remember we would like to reduce by dominance as far as we can, but we get to a point at times where we can no longer reduce by dominance. All right, and that's what happened here. And what did we do? We solved using oddments. Sorry. All right, we found those by using oddments. All right, and then figuring out the expected value based on those optimal strategy solutions. All right, and last things last. Oh, and I didn't actually put this in the PowerPoint, but there's another problem here that they give us in the notebook. 7 police versus 5 guerrillas, and notice that those are laid out correctly. And if you look through those, you'll see, yes, those expected values are shown correctly, but police 6-1 and police 7-0 are dominated by what? By police 5-2. Because the police break even all 3 times when they play their 5-2 strategy. Okay. And a half, a half, a half beats all of the ones below it. Why? Because there are zeros in some of those. So we get to a situation, right, where we've eliminated 2 rows. Now looking at the columns, there's domination. Why? Well, 0, 1/2 dominates 1/2, 1/2. Oh, and 0, 1/2 dominates 1, 1/2. Okay, so the guerrillas will only play 5, and therefore the police will choose 1/2, right? So the police always play 5-2, the guerrillas always play 5-1, and the value of the game is 1/2. And I'm not going to write that out. You should take some time and type that out in this notebook. But that is, this one reduces by dominance to the solution. We don't have to do oddments. I'll be back with another look at police versus guerrillas soon. Talk to you then.